In this video, I'm gonna talk about the heat effects of welding, which is a very important topic for welding procedures. To begin, first I talk about the other joining processes, for example, mechanical joining methods, to have a comparison with welding. Mechanical joining processes are classified into two groups: force locking mechanism and form locking mechanism. The force locking mechanism includes riveting, screwing, and wedge joining, and the form locking includes seaming, lapping, and clinching. Here you can see the form locking, force locking processes, and here you can see the schematic of form locking processes. In all mechanical joining processes, whether it is force locking or form locking, we don't have any heat effect in the structure. We have only plastic deformation, and this plastic deformation causes a mechanical locking between the adjoints. And the main disadvantage of mechanical joining processes is that we have weight addition to the structure. For example, here you can see the weight that we add here in the seaming process. You can see that we have 4 layers, and here for force locking processes we have addition of weight because of the lap joining that we have, and also the additional materials that we have here. The main advantage of welding processes is that in welding we don't add a significant weight to the structure. We have only a slight weight addition to the structure. Welding processes are classified into two groups: fusion welding processes and pressure welding processes. In fusion welding processes, we have the energy only in the form of heat. So, for example, melting and solidification, which results in a union between the two materials, and welding. In pressure welding processes, the energy is supplied in the form of pressure or pressure and heat. And you can see that we have the application of pressure, and we may have fusion, or we may have some plastic deformation. It depends on the process that we use. The main effect of welding is the heat that we introduce to the structure, whether it is this group or this is this group. The main effects of the heat of the welding processes are change of the microstructure, distortion and dimension change, and the residual stress. The distortion and the residual stresses are concerned in the whole of the structure. Residual stress we have concern especially near to the welding region here, and the distortion is concerned in the whole structure. And the change of the microstructure we are concerned mainly close to the fusion zone. In every location, we with respect to the welding center, we have a temperature time history. For example, in this location, in the red line, we have this curve heating, staying at the peak temperature and cooling. And also for the other points which are farther from the welding region, we have these time temperature curves. The main characteristics of the temperature history are high heating rate, high cooling rate, and short duration at peak, which is special to welding process. The main parameter that determines the temperature time history is the heat intensity of the process that we use. As comparison, in this table we have 3 welding processes, and you can see the heat intensity that we have for each process. For manual welding we have the least heat intensity, and for laser welding we have the highest heat intensity. You can see the schematic of the laser welding and MIG welding and how the heat is distributed in the workpiece for both procedures. The other parameter that is influenced by heat intensity is the temperature gradient that we have during the welding process. Here we have temperature versus the distance from the welding center, and this temperature is the maximum temperature that we have in each point. And we compared 3 welding processes: plasma arc welding, shielded metal arc welding, and oxy-fuel welding. For oxy-fuel welding, we have a smoother gradient of temperature, and for plasma arc welding, we have a steep gradient of the temperature. And these temperature distance gradient determines the extent of the heat affected zone that we have. The heat affected zone is defined by a temperature over which we have some microstructural changes. For example, imagine that we have this critical temperature, and by this critical temperature we can determine the extent of heat affected zone for every process. For plasma arc welding we have this extent of has, for shielded metal arc welding we have this, and for oxy-fuel welding we have this. And as you can see, we have a larger heat affected zone for oxy-fuel welding. The higher heat intensity of the welding process leads to higher cooling rate, smaller heat affected zone, and lower distortion, which is favored in so many cases. Another characteristic that we can define for every welding process is the isotherm that we have during the welding. The isotherms are defined by lines that specify temperature during welding around the heat source. For example, this curve represents the regions that have temperature, for example, 600, and this curve represents the locations which have temperature of 500, and so on. The closer these lines are, the higher the heat intensity is. With lower heat intensity, these lines are farther from each other, and you can have a sense on how the heat affected zone is greater in this process. The most important parameter in the temperature time history is the cooling rate that we have, and also the peak temperature, the heat, and the heating rate are also important, but not as important as the cooling rate. During the welding process we have a high heating rate, and also we have a short duration at peak temperature, which causes some phenomena. For example, we have some carbon which is not dissolved completely. We have some undissolved carbides. We have very large grains to the adjacent to the welding zone here, which is due to the high temperature that we have. And also we have the heterogeneous austenite, which is because of the short time that we have at the heat maximum temperature, and it inhibits the complete dissolution of the phases that we have. For the cooling rate, we can for structural steels, the most important temperatures are 800 and 500. During this between these temperatures, most of the microstructural changes occur, and that is why we define time, which is defined time by which the material cools from 800 to 500, and because of that we can define the cooling rate by this equation. The fast heating and cooling rate in welding makes experimental measurements very difficult to measure the temperature in every location, and because of that we use simulation approaches to calculate the temperature in each location. Thank you for your attention. If you have any question, you can communicate with me through this email or through the comments.